Welcome to the Runtime Vertex Color Paint and Detection plugin tutorial. This tutorial will cover all the features of the plugin, to give you a better understanding of how it works and what you can do. We will use the free example project as a reference, as it covers much of what you can do. Download link is in the description. The documentation covers all of these things as well, and goes into even more detail. Link in the description. The plugin makes it possible to paint vertex colors in runtime on static, spline, and skeletal meshes. You can do so in several different ways, which can enable game modes, mechanics, or just extreme audio-visual fidelity. The plugin supports both regular and merged skeletal meshes as well. You can also detect vertex colors in runtime, and get information of the closest vertex from a hit location, as well as information on, or, very close to that hit location, which is useful on meshes with few vertices. You can also get the vertex colors, physics surface of each channel, the material, UVs and the colors of each bone, colors as serialized JSON string, and more. The more vertices the mesh has, the more detail you get, but the task will take longer to calculate. But a good material can also make a big difference in how good it looks with fewer vertices. Remember that even vertex density is also important, if you want to make it look good evenly all over the mesh. If you have trouble finding a function, you can always right-click in the graph and look for it in the categories. Since this plugin launched, we've moved essential functions into custom nodes, so any references to subsystems in the tutorial can be disregarded. When working with vertex colors, it may be much more comfortable to have a mesh's default colors be at 0, 0, 0, 0, so if you spawn it, you know it will already be cleaned. There are two ways you can do this. First, when you import a mesh, you can in the import window, choose to override the vertex colors. There you can override them to 0, 0, 0, 0. So any instance of the mesh will be clean by default. The other way is useful if you've already imported the mesh. Then you can use the editor's own mesh painting tool, and set the erase color alpha to 0. Then simply remove all of the colors over the entire mesh by holding Shift and left-clicking. Then press Apply to apply it to the source, so any instances of that static mesh will be cleaned. To quickly get started with the most common type, paint at location, we're first going to make a simple material that makes use of vertex colors. If you want the channels to mix with each other rather than replace, then you can use add instead of just lerp. Now we set this material to be used by a static mesh, and set the mesh to be CPU access true, so we have access to data in vertex buffers. Drag out the mesh into the scene, and remove all current vertex colors on it so it's completely clean. Don't forget to do it for the alpha channel as well. You can also click Apply to have vertex colors be propagated to the source mesh, so any new instance of that mesh that you drag out will be clean by default. Now add a simple line trace in our playable pawn, toward where the camera is pointing, and hook it up to some input, so when we press a key, we can run the line trace. Then we add the component to your blueprint, and drag it out into the graph. Then from that, drag out and search for paint on mesh at location. Right-click and split the struct and connect the results of the line trace into the parameters, and set area of effect, fall off and strength of colors to apply. Now start playing. Look at the mesh that is using the material you just created, and press the input that you added. You should see that it adds color to the mesh at the line traces hit location. If you want to be able to paint over several meshes at the same time, for example to hide any seams, if there are several floor meshes next to each other, then you can use the multi-capsule trace for closest to unique meshes function. With it you can paint at location, on all mesh components within that area, based off of one location. In the example project there is a splaboon level setup with multiple floors that showcases this very well. The engine's own set static mesh and set skeletal mesh functions don't properly update the things the plugin uses, such as amount of vertex colors or amount of LODs. Set skeletal mesh even causes a crash if called after overriding vertex colors, even when using the engine's own set vertex color override. Because of this, we had to make our own wrapper functions that do some extra logic before running set static mesh and set skeletal mesh. So if you want to change static mesh, you call set static mesh and release override vertex colors. If you want to change skeletal mesh, you call set skeletal mesh and release resources. Then you can paint vertex colors and switch meshes whenever you want. To quickly get started with the get closest vertex data, we're first going to make a simple material that makes use of vertex colors. If you want the channels to mix with each other rather than replace, then you can use add instead of just lerp. Now we set this material to be used by a static mesh, and set the mesh to be CPU access true. Drag out the mesh into the scene and using the editor's own mesh paint tool, paint some colors on them for each channel. Now add a simple line trace in our playable pawn, toward where the camera is pointing, and hook it up to some input, so when we press a key, we can run the line trace. Then we add the component to your blueprint, and drag it out into the graph. Then from that, drag out and search for Get Closest Vertex Data on Mesh. Right-click and split the struct and connect the results of the line trace into the parameters. Select the component and set Print Logs to Screen to True, so we can see the results of the detection. Now start playing. Look at the mesh that is using the material you just created, and press the input that you added. You should get a print on the screen, with the vertex color values almost at the top. The rest of the steps is to register the material in the editor widget, so we can also get what physics surface is on each of the vertex color channels. Go into the plugins folder, and copy the vertex color materials template data asset, and place it somewhere in your projects folder, and name it something more relevant to your project. Then go into the plugins editor widget, which can be accessed by pressing the button at the toolbar. Then go into the Detection tab. Set it to use the data asset that you just created, and add the material you've made with vertex colors into it. Then set what physics surface it should be at each of its color channels, for example water, sand, snow, and mud. Now start playing and detect on the mesh again. Now you should be able to see, for example, water, 1 in value. You can utilize these results for sound or visual effects if you select the component, and scroll all the way down and add the Get Closest Vertex Data on Mesh delegate. It returns the results of the task, which is very useful. There is also a Get All Vertex Colors only if you are only interested in them, and not the closest vertex data. Color snippets can be very useful since you can store how your character should look like in a level or cutscene, or if you want to make several variations of enemies, like zombies, and how their wounds and blood looks. You can preview a created color snippet and update the colors if you want to make any changes, as well as update the snippet ID. When previewing a snippet, you can make changes, and then update the snippet with the new colors. You can get all available color snippets of a mesh in a few different ways, and is useful if you want to spawn zombies or something similar, where each should have a unique color snippet. Color snippets make use of gameplay tags, so you don't have to remember what the snippets are called when setting up the node. You can just select it from the tag list, or select the category you want to randomize from. Remember to remove all references of a snippet if you want to remove it from the editor widget. Start by going into the plugins root folder in the content browser, and copy the color snippet reference data asset, and the color snippet data asset template into your project. Name the reference data asset to something that fits your project. This is the data asset that we use to look up which color snippet data asset that has the vertex colors stored, and that we should bring into memory. Now name the color snippet data asset to what you intend to store on it, for example zombie variations, or main character snippets. In the editor widget, set to use the reference data asset, and color snippet data asset, then select a static or skeletal mesh that has vertex colors on it, that you wish to store as a snippet. Enter a snippet ID, for example cutscene 3, main character, and then click Add Colors to be stored as a snippet. Which mesh a snippet belongs to is visible when you hover over the list of snippets on the drop-down menu. In the Detection Settings tab, you can register what physics surfaces are on each color channel of a material. So when you detect on location on a mesh that is using the material, you can get the physics surfaces as well. In conjunction with the color values, this can be used to run logic, such as spawning sound or visual effects. Start by going into the plugin's root folder, and copy the Vertex Color Materials template data asset, and place it in your project folder, and rename it to something that fits it. In the Detection tab, set it to use the data asset you've just copied. Now simply add materials that utilize vertex colors, and set what physics surface is on each of the channels. For example, if the blue channel paints puddles, then mark it as puddle. You can add new physics surfaces in the project settings, under the physics category. You may have to restart the editor for them to become visible. Note that you don't have to add each material instance. You can add the material parent if you know that all the instances will have the same physics surface on each channel. You can choose to include the default channel here, so you get that as well when detecting. For example, if cobble is the default surface when no colors are painted, and you've painted puddle on top of it, it will return 0.5 cobble, and 0.5 puddle, if you included the default. Otherwise it will return 1 for puddle. If the painted colors completely cover the default surface rather than blend with it, then you should not include the default. You can register material instances as well, and set them to have different physics surfaces from the parent. This makes it possible for one parent material to have more than 4 surfaces, as long as the instance of that material can tweak the result of the color channel, so it can look like a different surface. With a registered material selected, you can further down in the Detection tab, add if any surfaces on the channels can blend into each other, and form another physics surface. For instance, if sand and water can become mud, if they're painted over a minimum amount. This is then used when we run paint at location, or get closest vertex data, when getting the most dominant physics surface at the closest vertex. In the Optimization tab, you can optimize vertex painting, by limiting the amount of LODs you paint on skeletal and static meshes. This can make a very big difference, since there may be much fewer vertices that you have to loop through. For instance, your main character might only need to be painted up to LOD1 if it's always close to the screen. Start by going into the plugin's root folder from the content browser, and copy the optimization data asset template into your project, and rename it something that fits it. Then in the Optimization tab, simply select that data asset to be used. Now you can select meshes with multiple LODs you wish to optimize, and just add them to the data asset. If you ever need to paint more or less than the limit you've set here, you can for each paint job override the LOD to paint up to, as long as you have access to that LOD, which you do for skeletal meshes or static meshes with CPU access set to true. The Runtime Vertex Paint and Detection component is the component that enables painting and detection. It can be added to blueprints, and can even be added in Runtime, which is useful if you just want to use it temporarily, like on skeletal mesh actors in a cutscene sequence. The component has several events for detection and its different paint types. If you want to run several detections or paint jobs at the same time for different things, it is recommended to add several components to the blueprint, so each can have their own event run. For example, one for footstep detection, another for drying the character if they get wet. When starting a new task, you can opt to send in additional data that you want to utilize when the task is finished, instead of having to cache some global variables. This is useful if, for instance, something is colliding with a wall, and you want to spawn FX based on the hit impulse and the detected physics surface, then you can pass through the hit impulse in the additional data struct. So when get closest vertex data event is finished, and you have access to the detected physics surface, you can then run the FX using the physics surface and the impulse. You can get the amount of tasks initiated by a component with get current tasks initiated by component. This can be used to check if a component has tasks queued up and is waiting to be finished. Get closest vertex data on mesh makes it possible to get the data of the closest vertex to a hit location, as well as the color at, or very close to the hit location. You can also get the colors on each bone, and the amount of colors on each vertex color channel, which is useful if you're making something like Splaboon, where you need to know the amount in percent each color has on the mesh. You can also get the physics surfaces on the red, green, blue and alpha channel. In order to get the physics surface, you have to register the material in the Plugins Editor utility widget, which is covered in the Editor Widget section of this tutorial. It returns the most dominant physics surface, and it will also check if there are any surfaces that can blend into a new surface. For instance, if puddle and sand should become mud. As with all detect and paint jobs, it can also return all vertex colors, positions and normals if set to do so in the callback settings. First, add the component to a blueprint, then drag out that component into the graph. Then from that, drag out and search for Get Closest Vertex Data on Mesh. Right-click and split the struct, and connect the result from a line trace. Through the Get Closest Vertex Data on Mesh callback event, that can be added from the component, the user can get the colors, position, normal, and the UVs of the closest vertex. You can also get the estimated color on hit location, amount of colors on each vertex color channel, as well as the colors of bones. This can be useful if you want to run logic depending on the colors of the bones. For instance, if you have a boss fight, where the player can freeze their limbs or something similar, and if frozen over a certain limit, the limb can break. When running detection with Get Closest Vertex Data on Mesh, we only loop through the vertices of LOD0. It can thus be much cheaper to run compared to paint jobs, if the mesh has several LODs. If running Get All Vertex Colors only, then by default we don't have to loop through the vertices to get the colors, which makes the task much faster, and is recommended if you only need all of the colors and not the closest vertex color to a hit location. However, if we set in the callback settings to include positions, normals, amount of color for each vertex channel, or colors of bones, then it will still loop through all of the vertices so it can get the data the user has specified that they want. Paint at location with area of effect and falloff will likely be the paint type that will be the most common. This can be used to create new game modes, gameplay mechanics, or just nice attention to detail. First, add the component to a blueprint, then drag out the component into the graph. Then from that, drag out and search for paint on mesh at location. Right-click and split the struct, and connect the result from a line trace. Set the strength to apply on colors between -1 and 1, as well as if you should add to the existing vertex color, or if it should get set to become something. Minus will remove color on that channel. You can also limit the paint color, so the colors applied don't go past a certain limit. This is useful if you, for instance, have light rain, that should make characters slightly wet, and never fully drenched. You can also specify which vertex normals that should get affected, within the area of effect. It checks vertex normals on the mesh within the area, and if it's within a certain dot to the hit points normal. By default, skeletal meshes have -1 set, which means all vertex colors within the area on the skeletal mesh will get painted. For example, if a paint grenade explodes in front of a character, both the front and back of the character will get painted. If set to 0, then only the vertices in front of the character would get painted. Static meshes have a default of -0.1, so vertices around corners of geometry can get painted as well. You can also override the LOD to paint, if you for instance only want to paint on LOD 0, to have faster calculations. Note that you can only override to LODs that are available on the mesh. If you try to override higher than what's available, the max LOD will be the one you override to. You can opt to run a detection, before, and after, the paint at location task. This is useful if you for instance want to run sound effects based off the mesh colors before changing them. For example, if a raindrop falls on a dry cap, it can make a different sound, compared to after it has made the cap wet. You can also get the colors as a serialized JSON string, instead of a T array of F color, which can be useful with web services. You can also paint using set mesh colors with serialized string, which will deserialize the string on the async thread and then apply them. With multi-capsule trace for closest unique meshes, you can paint on several meshes within the area of effect, to avoid any visible seams, for example floors. With paint jobs you can set it so only vertices, that has a certain vertex normal toward a world location, or actor, will get painted. You set this by setting the dot product minimum, where if 1, then the vertex normal has to point straight at the location, if 0 then it can be from the side and forward, and if -1 then within any angle, although if -1 then it defeats the purpose of using this. This is simply a cheap way of giving the developer control of which vertices that should get painted, for instance if only vertices directly to the side of a mesh should only get painted, or if you have a hollow sphere and only vertices on the inside of the sphere should get painted. There is more information about paint at location, in the documentation. Paint within area will apply paint on the part of the mesh that is within the bounds of one or several mesh or collision components. It supports cube, rectangle, and sphere shapes. These shapes are the cheapest, and also support extra extent. With extra extent we can apply colors outside of the area as well. For instance, if a character's clothes should soak up water if they're standing in a lake. It also supports complex shapes, such as landscapes, skeletal meshes, or static meshes with any kind of shape. This makes the task take longer to finish since we run traces for each vertex, but makes it possible to paint exactly where the collision of the landscape, skeletal or static mesh is at. This can for instance be used to paint patterns. For example, if you have a static mesh, shaped as a butterfly, then you can apply vertex colors with the shape of a butterfly. This may require a high vertex count on the mesh you're trying to apply it to, in order to really see the detail of the pattern. First, add the component to a blueprint, then drag out the component into the graph. Then from that, drag out and search for paint within area. Right-click and split the struct, and make an array of the components you want to check if we are within, and the shape they should be. It also supports fall-off in a few different ways such as spherical from center, gradient downward, and gradient upward. You can also override the LOD to paint, if you for instance only want to paint on LOD 0, to have faster calculations. Note that you can only override to LODs that are available on the mesh. If you try to override higher than what's available, the max LOD will be the one you override to. You can also limit the paint color, so the colors applied don't go past a certain limit. There is more information about paint within area, in the documentation. Paint entire mesh, can just like the other paint jobs, add, or set, the color, but over the entire mesh. This can be very useful if you're spawning meshes, whose default colors are undesirable, and you want to clean them by setting them all to 0. Or if for instance you want to dry a character that has gotten wet, then you can paint entire mesh with add, and subtract on the color channel that makes the character wet. Setting an entire mesh to be a color is very fast, as we don't loop through any vertices but just applies the color, which is why it is optimal when spawning meshes that you want to clean. First, add the component to a blueprint, then drag out that component into the graph. Then from that, drag out and search for paint entire mesh. Right-click and split the struct, and set mesh to a color, instead of adding to it. You can also override the LOD to paint, if you for instance only want to paint on LOD 0, to have faster calculations. Note that you can only override to LODs that are available on the mesh. If you try to override higher than what's available, the max LOD will be the one you override to. You can also limit the paint color, so the colors applied don't go past a certain limit. You can also paint at random vertices all over the mesh. This is highly useful if you have rain, snow, or similar effects, and is much cheaper than using particle collisions with paint at location. You can choose to propagate LOD0 colors to the other LODs, instead of randomizing it on each LOD. This will make the colors match a little better, and make it look a bit better when you see the LOD change on the mesh. Color snippets can be very useful since you can store how your character should look like in a level or cutscene, or if you want to make several variations of enemies, like zombies, and how their wounds and blood looks. Check out the editor widget section on how to create, store, preview, and update color snippets. To paint a color snippet, first, add the component to a blueprint, then drag out the component into the graph. Then from that, drag out and search for Paint Color Snippet. Right-click and split the struct, and select the snippet that you want to paint, or the category you want to randomize from, if you know the mesh has any available snippets under that category. You can get all of the available color snippets of a mesh in a few different ways. This can also be called through Blueprint, and is useful if you want to spawn a zombie or something similar, and want to randomize which snippet it should get, to always be something unique. You can also apply vertex colors using physics surface instead of hard-coding what should be applied into the red, green, blue and alpha fields. This requires that materials are properly registered in the editor widget, with what physics surface, if any, is on each channel. What makes this really useful, is in combination with physics surface families. Then you don't have to paint with the specific surface the material has registered, but can paint with its parent or child, and it will get applied to whatever channel the parent, or child, is registered on. For example, if you've registered wet as a parent, and cobble puddle as a child, so it's a part of the wet family. Then if you have a character that has a material with basic things such as sand, mud, and wet registered. If that character walks on cobble puddle, and we try to paint on the character with cobble puddle, the system will see that it has the parent, wet, registered. So it can apply the colors to whatever channel wet is on. It's the same the other way around. If you for instance have a parent physics surface, like sand, and it has a child, cobble sand. If for example a vehicle with a wheel that is sandy, drives over the material, and tries to apply sand on it, the system can see that it has a child of sand, and applies color on whatever channel cobble sand is on. It also supports any blendable surfaces, like the example project's cobble mud, which is a mix of sand and water. By using this system, you don't have to hard set color values into the red, green, blue and alpha channels. You also don't have to sync all materials with what is on what channel. This means that if the physics surface isn't registered at all, no parent or child, then you have the option to not paint any colors at all, or fall back to whatever is set to red, green, blue, and alpha. You can also utilize paint conditions with this system, and opt to have a different paint strength on other channels. For example, if we were successful in painting water on for instance blue channel, then we can remove color on other channels, in case water should clean up whatever is on there. Physics surface families are useful not only for painting colors, but just if you want to check if a surface is part of a family. If you for instance want to spread electricity through anything that's metal, then you can use the Does Physics Surface Belong to Physics Surface Family node. So if you ever add more metallic surfaces, you don't have to jump around and update a bunch of blueprints, but can just register it to be a child of metal, and it will pass the check using that node. With all paint jobs where you set a paint strength to apply, you can set a condition the vertex has to reach, in order for it to become applied. This is very useful to give the developer more control of which vertices that should become painted. The first one is, if vertex color is within range, where you can set a min and max range the vertex color has to be in, and on which channel. This is useful if you for instance want to apply on the blue channel, but only if the red is over a certain limit, or if you want to utilize an unused vertex channel to mask out, where nothing should be allowed to get painted. For instance, if it's raining, and you're running, paint entire mesh with random vertices, but you don't want any vertices under rooftops to get painted, then you can in editor time paint under the rooftops with an unused color channel. Then have a condition, that only colors that doesn't have that channel painted will get painted, meaning that under the rooftops nothing will get wet. If vertex has line of sight, is a very useful paint condition if you only want to paint vertex colors on vertices that has direct line of sight to an actor, or location. For example the sun. So you can, for instance, only dry a character where the sun actually hits it. Since we can also set a value if we fail to reach the condition, you can have it so a character dries faster on parts that are in the sun, and slow if not. If vertex is on bone is a useful condition if you only want to paint on the specified bones, for instance if you have a boss fight, and throughout it you can remove armor on its limbs, and if so, you can freeze the limbs off or something similar. The plugin supports painting on skeletal meshes simulated cloth, just as expected, and for multiple LODs as well. Since hair can also be cloth, it can also get painted if it is set up correctly. Note that the plugin does not support proxy simulated meshes, like the one Wind Walker Echo has by default, so it is recommended that you create the cloth within the engine, as intended. To paint on cloth, you have to make sure the character's skeletal mesh component has its weight for parallel cloth set to true, as well as its cloth blend weight set to 1. The reason for this is because if it was for instance 0.25, then the positions we got in code were still as if it was 1. Which meant we couldn't apply colors accurately to what the players actually saw. If you select the component in the blueprint, you can in the Details tab check to debug vertex cloth positions, as well as the normals, to see the actual positions we do the calculations from. To see debug points, you have to run the paint or detection on the game thread, so you have to set the default use multi-threading option to false. In Unreal Engine 5 we can also change the cloth's physics with the new Chaos Cloth system, which means we can make capes etc. behave heavier if they for instance get wet. You can also combine color channels, so if it is also sandy, that would combine into mud, then it could make it even heavier than if it was just wet. To set up cloth physics support, you have to use Unreal Engine 5, with Chaos Cloth plugin enabled, and if you've upgraded from Unreal Engine 4, then you have to remake your cloth through the skeletal mesh editor, so it takes advantage of the Chaos Cloth system. Then go into the character blueprint, and implement the interface, Vertex Paint Detection Interface. With Get Skeletal Mesh Cloth Physics Settings, we return what the physics settings should be for each color channel, for each cloth. You have to keep track of which cloth is at what index, if a skeletal mesh has multiple cloths. The example project's character has an implementation of this, that you can use as an example. If you're unsure of the physics settings you want, you can just change the default cloth physics settings in the skeletal mesh. Like changing lift, to see if it fits the behavior you want when the cloth is fully colored on a channel. For example if it is fully wet on the blue channel. When you're happy with the behavior, just use those values in the interface implementation, and reset the default values. There is also a handy function in the plugin's function library called Set Chaos Cloth Physics, where you can set the cloth physics to be whatever you want, independently from what the vertex colors are. There is also Update Chaos Cloth Physics with existing colors, where it just updates the cloth physics based on its existing colors. This is useful if you have a pre-painted skeletal mesh that already has colors at begin play, or if it can somehow become painted by something else other than the plugin, but you still want its cloth physics to reflect the colors we are seeing. What each cloth physics setting does is available in the documentation, which has been copied from the source code. Highly recommend reading it, to get a better understanding of what each setting does. It also covers how to set up cloth LODs. The plugin also offers a cloth overlap component. This makes it possible to register overlaps of a cloth, which can then get painted. For example, if a character with a cape is standing next to a waterfall mesh, and the cape overlaps with the waterfall, add the cloth overlap component under a skeletal mesh component, and it will sphere trace on the vertices of the cloth. You can set the detail yourself in the Details tab, but it is recommended to have quite low detail as it will be more expensive if you do it on every single vertex. You can also set the size of the trace. If bigger, then it can easier register an overlap with something if the cloth comes close to it. It may be more optimized to a few traces, but with larger radiuses. It is currently run on the game thread, but multi-thread support will come to it in the future as well. The example project is available completely free, but it does require the plugin, and won't compile if you don't have it. It is the very same project that has been used to develop the plugin, and thus has many examples for many things the plugin can do. The project is built for multiplayer. Try it out if you plan on using the plugin for multiplayer games. Note though that these are just basic examples. It is recommended that you make your own implementation from scratch, that suits the needs of your game. When playing in the example project, you can see the controls instructions at the right side of the screen, which shows the different things you can do. You can also open up a debug menu by pressing M, where you can see the current paint and detection tasks. The Vertex Paint third-person character contains the most examples, such as footstep logic, painting color snippets, painting patterns, saving and loading vertex colors, and much more. The character is also set up to get its cloth physics affected in the Unreal Engine 5 version of the example project, using the Vertex Paint Detection interface, with Get Skeletal Mesh Cloth Physics settings. In the Unreal Engine 5 version of the project, you can also go into the character's skeletal mesh if you want to see the default cloth physics settings. The fire example is an actor that will get spawned if you shoot onto flammable surfaces, such as oil. During its lifetime it will increase the size of its fire particle, and trace for nearby flammable surfaces between intervals. It can spread around corners, and to opposite walls, and even onto skeletal meshes. When it reaches a certain scale, it will trace around and downward, toward the surface it is at. If no hit, it will then trace inward, if there is anything flammable around corners. It will also do traces for surrounding surfaces and a line sphere trace, meaning it will loop and line trace, in the shape of a sphere. This was necessary since regular sphere traces, or multi-sphere traces, don't return the hit results on every single point of a mesh. If it gets a hit on a flammable surface, it spawns another fire actor, which has a sphere collision, which will block any other traces from other fires, so fires can't get spawned too close to each other. For skeletal meshes, we had to do inward traces as well, in order to be able to get hits on the opposite side of the skeleton, for it to be able to spread all over the body. For example, if the fire is spawned on a knee, it does an inward trace that can hit the head or neck. The flammable surface could for example be vines, moss, or whatever your game requires. You can set Show Debug Traces to True, if you want to see in more detail how the traces works. The traces are run on the game thread, which makes the fire pretty expensive. The fire particle is from the starter content, and is also quite expensive. The Paint Within Area blueprint is an example that holds logic if something overlaps it, where it loops through the actors and meshes that are overlapping it. It paints on them with Paint Within Area, where each of its children has a different shape. The cube, rectangle and sphere shapes are the cheapest and most recommended to use. By default it's set up to start a new task when the previous is finished. But you can choose to have it run on tick as well, which may be preferred if the area is moving fast. In the character there is a Save and Load Vertex Colors example, that runs, Get Mesh Painted Since Session Start. This gets a cached T-map of the meshes that's been painted since the session started. We can use this to run detection and get what colors they now have, so you can save them. You can clear this cached T-map with Clear Meshes Painted Since Session Start, which can be useful if you're going back to a main menu, or something similar. Note that this Save and Load example saves all of the colors, which may get heavy and may not even be necessary. A more optimal solution is to save the events that you finished in your game, and redo paint jobs based on that. For instance, if Remove Graffiti Mission is finished, then when loading, you run paint at location and remove the graffiti from that mesh, because the event is finished. The water drip gets spawned when you shoot a water paintball on a surface by pressing E. When it drips down, it paints water where it is now, while running a detection ahead of where it is going. If it goes over water, then the drip doesn't shrink, but rather increases up to its max size again, so it can continue further, through a watery surface, just like a real water drop does. What's unique about the water drip, is that it runs a detection before the paint at location, and that the detection is run on a different hit location, since it needs to check the colors ahead of where the drip is going. This makes it so we can do the entire effect with just one paint at location, instead of two tasks. The same drip is used with the graffiti example, where if you paint too slowly, a drip will spawn, but with different settings compared to the drip that gets spawned from a paintball. The example project has vehicles included and set up with wheel paint logic. The vehicles themselves have very little modification, just which static mesh to use as wheels, box collision for painting the ground, which material and size they should have, as well as collision settings. Each wheel was also renamed to fit a paint component that will get associated with it. The example project features a wheel paint component, that is a child of the regular vertex paint component. But with added logic to paint an associated wheel, spawn FX, and paint the surface under the wheel. You can customize the component extensively, so it works for wheels of any size. The components are also independent from each other, meaning you can have a vehicle with any number of wheels, like motorcycles and trucks, and specify which should spawn FX, and paint the surface, etc. If the surface under the wheels are very heavy, then it may be optimal to only have the back wheels set to spawn FX and paint the floor. You can override the friction as well, so even if driving over a static mesh, you can make it slippery if over, for instance, oil. You can read more about the vehicle wheel paint component, and how to set it up in the documentation. The example project also has several drawing examples, such as drawing on a really small paper, whiteboard, and graffiti wall. They are set up where each one utilizes a bunch of small meshes, so that instead of having one big mesh with, for instance, 250,000 vertices, they can have 4 with 66,000 each, so each task goes faster to finish, which is what you want with the drawing mechanic. It also has one that compares the colors from one wall to another by linking up the meshes and comparing them when you paint. This is useful for stuff like tutorials, so you can check how closely the player has painted a pattern or something similar. In order to handle fast-moving motions, we use adjust box collision to fit area between paint at locations function, so if the paint at location between two frames is too big, it will use a box collision, and set it to fit the area between those locations. Then we run paint within area to fill it up, so even if making extremely fast motions, it will look natural, as long as the delay between frames is 0, or not too big. In the example project, we also provide an example of how you can sync up both heavy and light meshes, if using paint entire mesh randomly on both of them, since a task for a light mesh becomes finished much faster than a heavy mesh. This is useful if you have an entire scene with meshes, some heavy and some light, and don't want the light mesh to get painted quicker than the heavy mesh, if you have a setup where you start the next task when the previous is finished. In the example project, you can make your character go into physics and roll around, and have them get painted by the hit event of the skeletal mesh component. This may be useful if you have a game where the character can get knocked away, and should roll over the ground briefly. What affects the speed of your task the most is the amount of vertices and LODs the mesh has. There are a few ways you can optimize the tasks. Firstly, you should leave the default use multi-threading option in the paint and detect nodes to true. This will offload the work from the game thread so the FPS is barely affected, even when painting on meshes that have 1 million vertices. The drawback is that the task may not get finished immediately as it does with the game thread. If you're painting and detecting on light meshes, and really want to make sure the callback event is run immediately, then use multi-threading option can be false. Also, don't have more vertices than you actually need. The cheaper your models are, the faster the calculations will be, but at the loss of precision. But you may not need as much precision, since a good material can make things look much better with fewer vertices, so recommend doing your tests with a proper material. Another way is to limit the default amount of LODs that you paint on skeletal or static meshes in the Editor Widgets Optimization tab, so we don't loop through as many LODs, and thus as many vertices, as we've previously covered in the Editor Widgets section of this tutorial. Another way to optimize if you're painting at location and want to detect at the same time. Then you can choose on the Paint at Location node to detect before or after the paint at location is run, which saves a lot of performance since you only have to loop through the vertices once instead of twice, and only add one task to the task queue instead of two. You can choose to detect at a separate location as well, meaning if you have a paint drop on a surface, you can detect ahead of where the drop is going, while also painting where the drop is right now. Another way, which is useful if you're detecting and only want to get all of the vertex colors, and not the closest vertex color to a hit location. Then you can run Get Vertex Colors only instead of Get Closest Vertex Colors, which will just get the colors from LOD0, and not loop through the vertices, which makes it very fast, unless the user in the callback settings have changed to return positions, normals, colors of bones, etc. Then it will have to loop through all of the vertices to get that. You can also save performance by making sure that you only paint the maximum amount of times you actually need to. If you want to paint on something often, it's recommended to only add the next paint job when the current task has finished, by checking if the paint component has any active tasks in tick, like in the example project. That way you have some level of control over the task queue, so it can't get out of hand, and add tasks before the first one is finished. So if you want it to feel snappy and responsive, you don't want the task queue to grow too large. Calculating tasks is much faster on shipping builds, so recommend packaging one of those to test out performance. You can call Get Calculate Colors Task Amount, which returns the meshes that have queues, and their task amount, that you can use in your debug tools. The plugin's own debug widget uses it. You can do much more with vertex colors than just paint surfaces for visual detail. They can be used to create game modes like Splaboon, or gameplay like Super Mario Sunshine. You can spawn particles, run sound effects, and run animations. You can even drive particles with vertex colors in Niagara. Hopefully with this plugin, users can explore and discover even more things to do with vertex colors, now that you can finally manipulate them in runtime like never before. If something doesn't seem to work, set the component's print to screen debug option to true. Then check the documentation for the paint type you're trying to do, as well as the troubleshooting section, which will be continually updated. Thanks for watching the tutorial. If you need support, or want to keep up with the latest news, you can join the official Discord with the link in the description.